So today we have Chelsea Bartram from University of Washington here to talk to us about a bird's eye view of wave-like dark matter. So Chelsea is coming from the University of Washington. She originally did her bachelor study at Boston University, where she worked on neutrino oscillation experiments to T2K. She then did her graduate research at the University of North Carolina, Chapel Hill, where she worked on the I'll try to say it correctly, the Calliope experiment, doing CPT violation using orthopositronium. She then moved on and did her postdoc at the University of Washington on the ADMX experiment, and is actually now transitioning to SLAC as a Panofsky Fellow, where she'll continue working on Axion Dark Matter experiment ADMX, as well as some other things like DM radio and some other work that I assume we'll talk about some today. So with that, we're really happy that Chelsea was able to come out and talk and take it away.
Thank you so much. So thanks, Mike. As you said, my talk is called A Bird's Eye View of Wave-like Dark Matter, and I'll expound upon what I mean by that in a few slides. And I'd just like to point out the error that I just noticed I made. I'm apparently still stuck in 2020, but aren't we all? So I'll continue and give you an explanation of what I mean by wave-like dark matter. So the official wave-like dark matter that people kind of agreed upon at the recent SNOMAS meeting out in Seattle is that we're calling all dark matter with a mass of less than 1 eV as wave-like. So it fits into several broad categories. So this we're referring to as pseudoscalar dark matter, scalar, and vector. Its cosmological production mechanism is what's known as the athermal and misalignment mechanism. More on that later. And its detection is primary means of detection is currently using the coherent interaction of the wave with a detector. And key to this is to use what's known as resonant amplification. So I'll describe more about that later in my talk. What do I mean by wave-like dark matter is that it primarily behaves like a wave. So you can write the dark matter field. In this case, we're going to talk about something called the axion, but it has some frequency which is directly proportional to the mass of that dark matter and some associated. And so when you typically think of particle physics experiments, you're thinking more in terms of particles and actual sort of objects that can sort of bounce off of each other. But if you calculate the de Broglie wavelength of the axion or wave-like dark matter, you get something that's actually quite macroscopic in size. So here you can compare WIMP dark matter to the axion dark matter, and you can see it's different by over 13 orders of magnitude. So that's huge. All right, so we're really dealing with this macroscopic de Broglie wavelength, and that obviously impacts the types of experiments that we do to detect it. And so how do we go about doing this? Well, the wave-like dark matter, in our case, we're going to focus on the axion, but this is thought to convert into a photon in a magnetic field via some mechanism known as the inverse Primakov effect. And the wavelength of this conversion photon is about, say, on the order of a meter. And now this squares with the estimation of the de Broglie wavelength of the axion from earlier, where I was saying, that was on the order of maybe hundreds of meters. And so we're really dealing with microwave frequencies here. And again, that informs the type of detectors that we use. And this particular type of experiment is sensitive to what we call the axion photon coupling, or GA gamma gamma. So you'll see this on our plots. And there are other axion couplings that exist, but many of the experiments that are leveraging these couplings are still in the very early stages. And so I'd like to point out that the first sort of concept that was thought up to search for axions is known as the Haloscope. So here's a picture of our experiment, which is a haloscope. And those of you at the Wright lab are probably very familiar with this, as Haystack uses the same technique. But this was first conceptualized by Pierce Secudi, shown here. So you might be wondering, what are the theoretical constraints on the mass of the axion? So if you go to the lower bound of this diagram, you can see that going down to about 10 to the minus 22 eV or so, And this lower bound is set by the size of the dark matter halo of dwarf galaxies. So the thinking here is that you wouldn't have a wavelength that is bigger than the size of the galaxy itself. On the opposite side, you have an upper bound that is set by supernova 1987A and white dwarf cooling time. And you can see how these masses match up with the frequency of the conversion photon that you would be looking for with your detector on the bottom here in Hertz. And so it is fairly well established at this point that an Axion mass in the range of about 1 to 100 microeV can constitute the entirety of dark matter. And so that's this region right about here. So that's where our experiment is searching. And you can see it's sort of, there's also sort of two regions. There's a pre-inflationary axion and a post-inflationary axion. So we're sort of right here on the edge of the two. Now, there's something unique about the particular type of axion that we're looking for, which is that it solves something known as the strong CP problem. So what is the strong CP problem? If we measure a neutron electric dipole moment of what we call CP violation, and you can see a diagram of why that is here on the right-hand side. And so people have been looking for CP violation in neutron electric dipole moments because this would be indicative of CP violation in strong interactions. And so far, we have seen no such thing, despite the standard model seeming to allow this CP violation. So we've been looking, you can see here are measurements of the neutron electric dipole moment. The sensitivity is being pushed down and down and down, and still no dipole moment. Okay, so here's the limit here, actually 10 to the minus 26 or so. So this is quite strange because the standard model seems to point to the fact that we should have CP violation there. And theorists have been thinking about this for a while. In fact, there were two theorists, Helen Quinn and Roberto Pecci, who came up with what they call the PQ mechanism or Pecci-Quinn mechanism. And this was proposed as a solution to the strong CP problem. And then later on, there were two physicists, Weinberg and Wilczek, who pointed out that, in fact, if you really believe in the PQ mechanism, it actually predicts a pseudoscalar boson known as the QCD axion. So when I refer to, I just want to point out some nomenclature. There's sort of two terms that are used broadly in my field. So there's ALPS, which is axion-like particles, and these can be made in many higher order theories. And then there's also axions. And so this includes the QCD axion, which solves the strong CP problem, plus these ALPS. And wave-like dark matter is a bit more generic, but it includes the axion. Now, within the QCD axion, there are two classes of models. So there's the KSVZ model and the DFSZ model. And the DFSZ model is very interesting to the community because it can be included in grain unified theories, so gut scale theories. But unfortunately, it's also the most difficult to detect. And so my experiment has been on the leading edge of this for quite a long time. So we've been able to reach this DFSZ sensitivity. And so this is very exciting. More recently at Patras, some other axion search known as CAP was able to achieve DFSZ sensitivity, but it's very difficult to do. And so there remains a challenge to all of the community. Now, so what does the axion parametric space look like? So here you can see this is a plot showing the excluded regions, and you have it as a function of the coupling, so GA gamma gamma, axion photon coupling, and the mass of the axion shown here. And then you also have these this yellow band and these two lines, which is representative of the KSVZ and the DFSZ models. And you'll notice that there are a few experiments that are actually going down and touching that DFSZ line. So that includes on this plot just ADMX, and then it will include the very recent results from Patras. Now, how do we go about detecting the axion? As I stated before, its wave-like nature informs the detector that you use. And so right now, these Haloscope experiments are using this photon detection. So this is what we think is the cleanest channel for discovery. They leverage the inverse Prumkov effect, whereby the axion converts to a photon in a magnetic field. In this situation, we're dealing with microwave frequencies, and we're looking at this GA gamma gamma term. And so what you do is you use what's called a haloscope. So this is the resonant microwave cavity, where an axion comes in, it converts to a photon. And then this is essentially an electromagnetic field that you're sensing in the cavity with some receiver chain. Okay, so more specifically, what does this look like in the case of ADMX? So I'm showing this cartoon here, and you can see that there is, my laser is not working. Okay. You can see that there's a detector, and this detector is immersed, in our case, in an 8 Tesla magnetic field. So an axion comes in, converts to a photon, and that sloshing electric field is then picked up by an antenna, which is coupled to an ultra low noise receiver chain. So that signal then propagates through the receiver chain through multiple temperature stages, as the cavity itself is sunk to a dilution refrigerator, which maintains a temperature of about 100 millikelvin. So that signal is then amplified, digitized, and Fourier transformed to form a power spectrum. And so you can see a cartoon version of this on the right, where you have power as the y-axis and frequency as the x-axis. And because the signal is thought to be very small, we average over a number of spectrums to sort of build up a signal peak, which you can see in this cartoon. And so that would be our axion signal. And that signal is almost monochromatic in frequency, but has some associated line shape, what we call line shape. And this comes from the motion of the Earth through on its axis around the sun and through the galaxy. So this is showing a zoomed in version of what that axion line shape would be. And so you can see that it actually has what we call Maxwellian line shape. And then because the Earth, again, is in motion on its own axis around the sun, there's some frequency modulation that if you took data for long enough, you would be able to observe. And so I had a student who worked on looking at different, oh, thank you, different line shapes and integrating these into our analysis. And just to give you a sense of what sort of the most typical line shape we would expect looks like, this animation shows the frequency modulation with the Maxwellian line shape, or we also call it velocity distribution. So that would be one way to possibly identify an axion signal. Sorry, this is just the frequency modulation from the rotational and orbital motion.
And what is the increase in probability at energy 0.5 PeV signify?
The 0.5?
Like, yeah, so I see that with the modulation, like the probability function. Yeah. So what does that signify at
so this is just, so you can do a calculation based off of where your detector is on the Earth and what latitude it's at. And then knowing that and sort of having some basic assumptions about what the velocity distribution is for the axions, you can compute how this line shape should change. So that's all this is doing. I don't know exactly why this point is higher at this time, but it's just making some very basic assumptions about what the velocity distribution looks like. And then because the axion mass is not known a priori, we have to have a tuning rod. So here you can see for our most recent run, there's 2 tuning rods that we move to adjust the frequency of the cavity resonance. Now, the size of the cavity roughly determines the frequency of the axion that you're sensitive to. But again, we put those tuning rods in there to sort of tune over some range for any given cavity. And the overlap of the axion electric field and the static magnetic field determines something we call the form factor. So that's this term here. And the axion couples to a mode with it couples most strongly to the lowest order mode. And this is equivalent to saying it couples to the mode which has the largest form factor. So that's the mode we're interested in as we tune our cavity, and that's the mode we want to track. Okay, but how does all this come together? So we have to basically package up what we call the insert. So that's the cavity and all the electronics I showed on the previous slides. And then we have to get that into our 8 Tesla magnet force. So here you can see, this was when I first showed up as a postdoc, we had to commission everything and get it into here. And the signal, once it's in the magnet board, is expected to be extremely low. So the Axion signal power is predicted to be on the order of about 10 to the minus 23 watts, which I believe is something like 2 bars of cell phone service if you're on Mars. So that's quite small. And we really need to leverage different technologies to achieve sensitivity to the signal. And so what do? Well, the first is we have to use a mixing chamber. So this is a dilution refrigerator that's mounted to the cavity. And this suppresses the physical noise temperature of the experiment. And then we also have to minimize our amplifier temperature. So we have a quantum amplifier package, and that is able to, that enables us to achieve noise that is close to the standard quantum limit. So what is that quantum amplifier? Well, it's something known as the Josephson parametric amplifier, or JPA. So again, this is critical to obtaining our low amplifier noise. It's essentially a parametric amplifier. And the classic example of this is a child on a swing. There's an anharmonicity in this amplifier that leads to energy transfer from the pump to the signal. And this Josephson junction is the key. So that's the nonlinear element. And so this all gets mounted in this very sophisticated package that we have that we call the Squidadel. So this is to ensure that it doesn't get damaged by the high magnetic fields, because these amplifiers are very sensitive to that. So we have mu metal, and then there's also a field cancellation coil that encloses this package, and that's required for optimal performance. Now, when you're actually running the search, you have to really optimize this JPA performance in the environment of the magnet board, since it's so sensitive to fields. So you have to be wary of things like magnetic flux penetration, vibrational effects from liquid helium fills, and changing temperatures. And so we are constantly characterizing it. I wrote many of the scripts to sort of generate these plots and verify that there are optimal biases at any given time. And so here you can see a picture of what it looks like on its own when it's not all wrapped up in the packaging. And so data taking operations is actually a complex series of events that occur, which is not, and it's not just the acquisition of Axion data. You always want to understand the state of your detector. And so I'll just briefly step through these. So the first, as I mentioned, is you want to bias your quantum amplifier. The next is you want to do a transmission measurement. So this tells you about the quality factor and the resonant frequency of your detector. You want to do reflection measurements to get the antenna coupling. You inject something called a synthetic axion. So I'm going to talk about this later. This is a tool ADMX uses in order to better understand our sensitivity. You then take Axion data. So there's Axion search data. And then move rods, couple the antenna, and start the process all over again. And so as a postdoc in this experiment, I developed the ADMX Control Software and a sequence of data taking steps. We have some which enable you to correlate events in the insert. So I worked to develop our web page shown here. All of our controls are leveraging this tool called Kubernetes, which allows for quick recovery of the system in the event of failures. So I was in charge of managing that as well. And then we have a dynamic analysis that interfaces with all these controls. So that tells us if we find a signal, then what do we do? Or if we don't have enough data, what do we do? And so that brings me to our Axion detection procedure. So then there's this question of if we see something that looks like a potential signal, we want to know, is it an axion? So we have a series of qualifications that every potential trigger or signal goes through. And we have to verify that that trigger is not, in fact, some fake signal in the detector. So this includes the signal cannot be radio frequency interference. So this is called RFI. So in other words, it can't be coming from some radio station that's just down the road. It has to be, the signal has to be persistent. So as I mentioned before, we take many power spectrum and average them together. So it has to appear persistently in all of the scans. It has to follow what's called the Lorentzian shape of the cavity. So the cavity is resonant, and so on resonance, we must see that the signal is enhanced, and off resonance, it must be diminished. As I mentioned before, the axion couples most strongly to the TM010 mode, so we have to verify that it is suppressed in non-TM010 modes. And then finally, we can check if the axion signal power varies as b squared. So if we manage to rule out the possibility that this is some noise or interference, we can ramp the magnet, and we can check that it in fact scales as b squared. And of course, we wouldn't want it to be one of our synthetic signals. We use that as a check on our sensitivity. And this is important because it makes sure that we understand what we're doing all along. So we have some blind injection team that injects a synthetic signal into the detector at different points in frequency space and doesn't tell the operator, like in this case it was me, that they're injecting anything. So you can see from our last run, there was actually the signal shown here, and we correctly flagged it in our analysis and said that looks like an axion. We went through all of these steps and eliminated these possible scenarios. And then at the end of the day, we said, okay, this looks like an axion, go and ramp the magnet. But then our blind injection team said, no, that's something we put in. So we got very excited and then found out it was not an axion. But it's good, we understand our experiment. I played a big role in building these tools to perform these tests and verify the candidates. Now, so this was the data that was acquired between 2019 and 2021. We were able to successfully rule out a large chunk of the parameter space. So you can see on this plot, the red is the most recent result. Orange is from the prior run, and then there's also blue, which was the first data set from ADMX at DFSZ sensitivity. So if you're interested, you can look at this paper on PRL, and you can read about how this data was acquired and exclusion set. Now, if we zoom out and we look at the wider parameter space, you can see ADMX has covered this region in green and more recently red. But there's a wide amount of parameter space that is yet to be explored. And of course, Haystack is up here as well. But I want to point out some ADMX high frequency efforts. So there's this green band up here and explain what that is. So this is what we call the ADMX sidecar. And so sidecar is a small prototyping cavity that sits on top of the main cavity. You can see in this picture. And it's testing a number of R&D efforts that ADMX is interested in the future. And so in this data taking run, we tested something called a traveling wave parametric amplifier, or a TUPA, which I'll explain in a bit. We also tested a particular type of cavity design. This is called a clamshell cavity. And then finally, piezo motors for the antenna and tuning rod. So all of these might be sort of rolled into ADMX high frequency efforts in the future. So we want to verify that we can make them work now. And we did that with this cavity sidecar. You can see a mode map of sidecar shown here. And probably the most interesting facet of this experiment is this traveling wave parametric amplifier. So this is a quantum amplifier similar to the JPA. But the interesting aspect of it is that it has broadband gain. So here you can see this is a reflection measurement, and you're measuring how much gain there is when you have the TUPA off versus on. the blue is with the tuba on. You can see there's about 15 to 20 dB gain across a very wide frequency range. So about 4 to 8 gigahertz or so. So this is wide compared to the JPA. JPA is only provides gain over a few hundred kilohertz or so. So that's very exciting for us. It's also very compact, and you optimize its performance with just some pump frequency that's provided, and you change the pump frequency and the power. Now, we were able to, I'll say we were able to demonstrate sensitivity to this region shown here on this plot using the JPA. This was posted on arXiv. We're actually modifying it because there's some recent experiments that have also been digging into this part of the parameter space. But it was a successful endeavor insofar as we demonstrated usage of a tupa in an Axion search. Okay, now for the final part of my talk, I'd like to talk about a broad challenge that is facing the Axion community right now, which is our ability to scan this parameter space. So any Haloscope search is limited insofar as the rate at which it can acquire data. And that limitation is defined by this equation. And essentially, the limitation is coming from the fact that you have a resonant cavity, and that only has some finite bandwidth over which it's sensitive to axions. Right, so here you have what we call the scan speed equation. And as an experimentalist, we can seek to sort of optimize the performance by changing various factors in this equation. So first, we could try to maximize the terms in red. So that's the magnetic field, the volume, the Q, and the form factor. And then we can try to minimize this yellow, these yellow terms. So that's our system noise. This is coming from our amplifiers and also the physical temperature of the experiment. And then finally, we can't control the dark matter frequency, coupling, or density. So sort of let nature pick that. Now, this leads me to what's called the Axion scaling challenge. So as ADMX or other Haloscope searches move to higher frequencies, they have to move to smaller volumes. And that slows down the scan rate because, as I showed on the previous slide, the scan rate is proportional to the volume. So we need solutions to this problem, and different groups are coming up with different solutions. So in the near term, ADMX plans to coherently combine the power from multiple small cavities to circumvent the scaling challenge. And so this will take place once we hit this 1 to 2 gigahertz region. So we aim to target DFSZ sensitivity in this frequency range. And we will do that with a 4-cavity array located at University of Washington, where I am now. And so the 4-cavity array will look something like this. Each cavity will have its own tuning rod. We'll have a coarse tuning rod and a fine tuning rod. And that will enable these all to tune synchronously. But the real secret is that by combining in cavities in phase, you can get a square root of n improvement in the signal to noise ratio. So that's our goal with combining these 4 cavities. And I'll be playing a role in this at my new position at SLAC. So I'll be involved in the development of the RF and quantum electronics for this, as well as data analysis. Moving on, we aim to cover this 2 to 4 gigahertz frequency range, which we're calling extended frequency range, or EFR. Again, the target will be DFSZ sensitivity. And this frequency range will come with its own unique complications. So this will again be a multi-cavity array. But one of the ways we aim to overcome the scaling problem is to use a stronger magnet. So we'll use this 9.4 Tesla magnet, which has a large bore. And we've started prototyping different cavities for this run. And as I stated, we'll need to severely scale up the number of cavities. So we're looking at potentially 18 cavity arrays. So here you can see they all kind of fit together in this honeycomb type of design. And here you can see a picture of what the individual cavities look like from my collaborators at University of Florida. And we've been running simulations to make sure we can actually maintain the scan speed that's desired. Now, ADMX EFR will be unique insofar as it's using, first off, this horizontal magnet that I showed on the previous slide. So we'll need a horizontal cryostat. One of the design features of this experiment is that we have some extra modularity. So this is exciting to me as someone who has run the experiment on site at UW. We plan to separate out the resonators, what we call the resonator dilution refrigerator, from the electronic solution refrigerator. So this is the dill fridge that maintains the low temperature on the cavities. And then this is the dill fridge that maintains the low temperature for the amplifier. This magnet has a very large bore of about 258 liters. So that's great because there's potential room for R&D work. And then we're looking into the possibility of implementing other techniques such as squeezing, which is something going on here at Yale, or superconducting cavities to boost the Q. So I've shown you one possible solution to this problem, but in the long term, we really need other solutions and come in. So there are a number of different ideas. You can, again, boost the quality factor, the field, minimize the system noise, boost the volume. So people are working on a variety of different concepts for this. But I'd like to propose one that will enable us to go broadband in the future. And it's what I'm calling resonant feedback. So the way I'll explain this is I'll state that in an ordinary cavity haloscope, you have some cavity that has resonance and some quality factor associated with it. And you can imagine that instead of that situation, you have just some electromagnetic structure with a high form factor. So remember, the Axion couples strongly to, in the case of a high form factor, it couples strongly with that structure. And then you have the signal routed through a filter and then routed back into the experiment. And so in this situation, this is what's known as feedback. And your quality factor is now, or sorry, the resonant frequency is now associated with this filter frequency. And so now what you can do is you can imagine implementing a number of filters in parallel, and you could generate a number of resonances in this detector volume shown here. So the exciting thing about that is that it would decouple the frequency from the Axiom conversion volume itself, and you would no longer have mechanical tuning. So these are two big barriers with the haloscope experiments. And then if you implement the filter on FPGA, you could have the ability to just program in a different frequency, quality factor, and phase for that filter. If you're curious about this, my collaborator Ed Daw wrote this paper that was published in NIM. And so, and so this is ultimately what we'd be aiming for. And so if you do this, you can imagine, you can substitute in some values in the scan speed equation that are relatively poor, but you can imagine increasing the number of resonances. And if you do that, you are no longer constrained by the limitation of a standard haloscope experiment. And so you could assume having 100 to 1,000 resonances, which is definitely possible on these FPGA boards. And you can potentially increase this scan speed by a factor of 100 or so. And so we did a test of this when I was a postdoc at UW. Here you can see what we did is we took power spectrum on the sidecar cavity, and we had feedback induced resonances on the sidecar cavity. So this low bump, this 500 hertz wide bump, is a resonance that was created using one of these filters on an FPGA board that was in a loop with the sidecar cavity. And then we injected synthetic signals, or I injected synthetic signal tones here, and demonstrated that the tones are enhanced on resonance and then they diminish off in much the same way you would have for an ordinary cavity experiment. So this was just a proof of concept that this could potentially work. And we used some very basic FPGA boards, but it was exciting nonetheless because it behaved in a similar way to cavity resonance. But there's much work yet to be done, and we want to sort of come up with a future version that will enable us to study this more in depth. So our first version used this Basis 3 FPGA board shown here, and it only had about 7 resonances that we could sustain at any time. And there were many auxiliary electronics, so mixing stages, filters, etc. Future versions, we're hoping to use a much faster board because the timing of the signal is important. We want to be able to have between 10 to 100 resonances, faster signal processing and onboard signal processing to use fewer auxiliary electronics. And so this has a number of possibilities. One of the exciting possibilities is that you're no longer tied to a typical cavity design. So we're detectors. We could have a large volume or a high form factor. And this was one such idea we came up with using different capacitor plates. And just to wrap things up, I'll be looking into this in my next position. There are a lot of synergies where I'll be working at SLAC with the FPGA expertise there. We're looking into using these so-called RFSoC boards, which have been used in CMB experiments, for example. In fact, we started looking at how to implement different algorithms on these boards already. Okay, so I'll just skip this slide. In general, where I'll be working at SLAC, there'll be a lot of other synergies as well. So they have a detector microfab facility, and that should coincide with the startup of many Axion searches when that comes online. So that'll be great for manufacturing these quantum devices, which is TUPAs and JPAs, as well as single microwave photon counters. There are people in our group that are interested in that as well. So in summary, I spent the last 3 years running the ADMX experiment at DFSZ sensitivity. I started to spearhead this resonant feedback technique, and there are plans to continue these ADMX high frequency efforts with my collaborators, as well as at SLAC, and as well as R&D plans for applying resonant feedback to upcoming searches. So thank you, that's all.
So thank you, Chelsea. It was an excellent talk. And so with that, I think we can open up for questions either virtually or in the room.
Sure.
A couple slides ago, I was wondering, why is the magnet going to be horizontal? I'm just so used to seeing vertical setups.
It's just a matter of what's available, really. So magnets are hard to come by. So you want to, and we're trying to optimize a few things, right? We try to optimize the field, most importantly, because the Axion power goes like E squared, and then the scan rate gets 3 to the 4th. And then the volume is important as well, because that also appeared in the scan speed equation. So it's sort of an optimization process between the two. But basically, this was available and it was a reasonable, I think, price for the ADMX experiment and also its location. So I think it was at UIC institution, and then they're migrating it to Fermi Labs soon.
It looks like an MRI.
It is, yeah.
It is an
MRI.
MRI. That's what I was gonna, yeah.
Is the Dilfridge vertical? Yes. Well, actually, wait, no, sorry. The Dilfridge, this is why we have this kind of funky setup. So it's actually horizontal. Sorry, the cryostat is vertical, or the cryostat is horizontal. But these are vertical.
Right, okay.
Yeah.
Reinforcement, so it's actual horizontal.
Yeah, that's interesting.
Right.
I actually don't know why they went with these vertical, but maybe it's just.
Dr. Kent, right? You have strong opinions. He has
Oh,
a
really?
horizontal.
Oh,
And
I saw that actually when I was there.
yeah.
Does he prefer it for some reason?
Well, no, so you do it for like not a lot of space stuff is all overhead, right? So it's easier to fit horizontal things. But then comes like you can't hang things, so that changes how you move things.
Well, I would imagine that would be the hardest thing is good thermal connection.
Yeah.
question was also on this picture because I don't think I understand, like, is it the case that all of the fridges and the magnet are all connected, like vacuum connected? Or are they like separate and then the electronics are what's connecting them?
So I think this is all vacuum connected to each of these, but the nice thing about this is that this can come out on its own, and if you want to mess around with electronics, you don't have to go inside the magnet. I don't know if that answers your question.
So is that's the benefit of having separate Dell fridges from the.
That was our biggest reason. So, well, I'm sure people in Haystack have, realized the same thing with the, with having a JPA in the magnet. It's such a pain to ramp every time you want to. If you just think you have a problem with the JPA, you just want to take out the JPA. So that would be great if it could be on its own, and you don't have to ramp the magnet. That's another thing with this magnet. They had it running and they couldn't. It took them a while to figure out how to ramp and ramp up and down, I guess, because it had just been running for a long time.
And then why are these two so separate? Why are the two of them fridges so separate from each other?
Here, just like why is this just
Yeah.
what it is?
Yeah.
That's a good point because it's interesting. I was talking to DM radio people, and it's why some of this stuff could never work with stuff. But yeah. So for us, there's not really any problem with doing that, given the frequencies we're looking at. So I think when you're asking like why not just cram it all down here because you'd have less loss. So I don't have dimensions. Yeah, that was probably the main reason, I'm guessing.
I see. So the electronics are far away as possible.
Yeah.
And then the resonator solution fridge, that's the thing that's connected to the cavities?
Yep.
Okay.
Yeah, you can barely see it, but there's like
So there's like some sort of thermal coupling between what's inside the magnet and what's in that fridge?
crystal.
Yeah. Yeah, that
Yeah,
I'm
this
just
is
trying to
thermally linked to the.
one. Okay.
Yeah, I don't know if you can see it really faint. There's copper bars.
And is that the only purpose of that fridge?
Yeah.
Okay, thank you. Thank you.
Just now realizing it says MRI magnet.
Oh,
I couldn't read it from over here, sorry.
No, it's fine. Yeah, sorry. I'll go on.
Yeah, so I'm just wondering how much of the analysis depends on modeling. For example, if the annual modulation signal is very different from what theorists expected, would that change your exclusion limits?
It's a good question. So I'll go back to keep thinking this does something. Yeah, so actually we sort of did some studies of this already. So you'll see here on any of our plots, there's like two colors. There's a darker color and a fainter color. And the darker is just sort of, it's called the Maxwellian line shape. So that's sort of very standard, sort of the most basic assumption you can make. And then we have another one called N-body, which was proposed by a theorist collaborator of ours. And so you can see it does change between the two. Yeah, so there are different models, but I think this one's pretty widely accepted. You have to look at the paper to see what assumptions he makes in this model, because I don't remember all of them. Sometimes when people write these, the assumption for the dark matter density is slightly different too, and that can make a big difference. So it's not just the line shape. A lot of times the person just made different assumptions because there's a lot of uncertainty in the dark matter density as well. So it's a little bit tricky to, the thing is no one really knows, right? So you just have to look up the model and look up what the assumptions are. Yeah.
I have two questions. First one is that do you have any preference of the orientation of the cavity? Because I assume we don't know the direction of the travel of the axions.
So with the axions, the assumption we're making for this here is that this is just ambient. So it's the isothermal halo model, and it's just that there's this sort of ambient dark matter that we're all just passing through. And so in that case, this orientation doesn't matter. There are some experiments where for wave like dark matter where it does matter. So like hidden photon searches, there's a polarization. I think it matters there, but Sumi doesn't know. You wrote the hidden photon paper, but for us, it doesn't. It's not that big of a.
Yeah. The second question is that you also show a next stage is a multi-cavity setup, arrays of cavities. Is there any chance to entangle them to improve the sensitivity from the classical limit to Heisenberg limit?
So is there any chance to entangle them? Is that what you said? To
Yes,
include
because square root
cats?
is not quite a good scaling.
No,
factor
it's
here.
It's not perfect, no.
Yeah.
So how would you, okay, so you're talking about entangling cavities. Is this like C-spire or something, or?
Like you
don't quite
entangle the not cavity cell, but entangle the microwave photons inside. Then the scaling factor can go to Heisenberg limit if one not a square of them, but a scale with n.
That's interesting. I'm aware that people do this in like the quantum, you know, with the quantum computing and stuff, but I don't quite understand how it would work in the case of Axiom. But do you want to talk after this maybe? And
I'm
if
also
you
not
have-
familiar with that,
okay.
but I'm keeping heard people talking about that, like Triple Ion community, they are using that a lot.
I'm not totally aware of how that would work in our case. I guess that's my, that's where I'm stuck. I don't know enough about it. I'm sorry.
I guess once you see something, well, I don't know. You could think of, like, not in a quantum state, but maybe you could be down on noise by requiring that.
Yeah.
You have one dimensional. But I think that power is not big enough. Probably, you know, to require like that.
I don't know. Yes. Okay.
Yeah, to go back to your sensitivity plot for the PRL,
Mhm.
I guess I never paid attention to these plots, but what happens in each frequency band that you scan that the sensitivity is and why there are some
Mhm.
peaks and
Yeah, it's a good point. So tuning these is not easy, as Mike will tell you. So there's such variation because you have a number of components in the receiver chain. There's a few reasons, but we're using these quantum amplifiers, right? So those are their gain and their noise performance can vary as a function of frequency. So that's one thing. And then additionally, you have other effects when you tune the cavity. So if you're just looking at the cavity itself, you know, your quality factor might vary as a function of frequency. Your coupling, your antenna coupling might vary. There's all sorts of stuff happening when you're running this. So you have to maintain everything at cryogenic temperatures. So you have to do things like liquid helium fills, or someone is working in the lab stomping around on the top of the detector, or you have, let me see, you know, depending on the magnetic field, your JPA gain might be worse or something. So there's a lot that's happening as you're tuning. And so that's why this varies as much as it does. Also, you'll notice that there's gaps, and that's because these cavities, if you look at the, if you do some RF simulation, you'll notice that there are what are called mode crossings. So I had a plot somewhere. There it is. So at the mode crossings, with anytime these lines cross, it's very hard to take data in those places because you want to track the lowest order mode. And then if you run into these other modes, you know, your fitting software stops working and you have to try to get back on track. So, and then it's not always as well understood in those regions as it is, you know, when you're right on the mode in terms of the RF simulation. So anyway, that's why it says rough and full of gaps. Yeah.
So I have a question about the two plot,
Yeah.
the amplifiers that you mentioned.
Yeah.
I'm just wondering, I guess compared to JPA, so this is very broadband, which is obviously a huge advantage, but did you notice any disadvantage compared to JPA?
Yeah, so the noise performance is not quite as great as a JPA. It's not that different, but it's just not quite as good. But the hit is sort of small relative to the amount of, the bandwidth. So depending on how you use it, that might be good. One of the things with the JPA is that because its bandwidth is so small, you have to constantly do, we call it chasing the bias parameters. So you're constantly like toggling, like, okay, how do I get the best gain? And you try to crank up the pump power, adjust the frequency. And that's frustrating, especially when you have this weird environment with the helium fills and the magnetic field. So the TUPA was pretty nice, and from my experience of operating it, because you kind of just set the bias and frequency, and it was very stable, and you didn't have to adjust anything constantly. So I like that a lot. We want to do more studies with it because we're not sure beyond that. If there are other advantages. We did have the magnetic field. We thought we had some flux penetration during the time we were taking data, and it got to the point where it was so bad the TUPA stopped working and the JPA. We were able to heat it back up, and that removes flux penetration, and then got it working again. So, and this may have been my imagination, but it seemed like the TUPA was giving us some good gain, even when the JPA was not working in that environment. Now they're not in the same location, so it could be that, but I was like, maybe it's more robust against the field. Yeah.
Who makes your
This was the Lincoln Lab. So Will Oliver. Sorry.
Yeah. Just quick on this. Are they phase sensitive amplifiers too, or are they phase insensitive? Like the JPA?
Yeah, I'm trying to remember.
It's not.
I'm sorry.
No, that's fine. I was just trying to
So we
think.
don't have, we don't supply it with a bias current, but you do that in both cases with phase sensitive and phase sensitive. So yeah, sorry, I don't.
No, it's fine. I was just curious.
Okay.
The resonant frequency feedback, would that still require some kind of manual tuning, or does the feedback take care of that?
Yeah, so that's another reason why I think it's an exciting idea, is because you can, let me go to the picture. The idea is you don't have any tuning rods or anything like that. The way you tune is this filter determines what frequency your resonance is at. So you put a bunch of these filters in a row, and then you don't have to tune. You just are at different frequencies for each of those. So yeah, this concept kind of comes from, it exists in like the radio world. So like there's something called a regenerative receiver. So that's sort of what it was inspired by.
Is there a point where, like, I don't know, if you wanted to like optimize the number of filters you have, like, is there a concern with, I don't know, like the just electrical noise you'd be introducing with everyone?
Yeah, so the only barrier to implementing like a billion filters is what you're implementing the filters on. So in that case, you're trying to put it on a field programmable gate array, so an FPGA. So this is basically like you can program this hardware to have sort of different electrical components. I don't know if you're familiar with FPGAs, but it's sort of like a computer you can program and tell it, I want a capacitor here, I want this here. So you can program an algorithm which basically is representative of a filter. So yeah, the limitation is what is the CPU of that FPGA, and also, yeah, you want to really understand the timing of how long it takes for the signal to go through the whole circuit, because okay, the Axion, so the way this situation works is the currents circulate around and they come back to the same point within something called the Axion coherence time. And that's really important for the power to build up in the cavity. It has to build up and build up. And that's why with a resonant detector like this, you get such a good signal to noise. When you don't have that, you need to make sure that your signal comes back around within the Axion coherence time to have the same effect. So that means whatever electronics you've got going on over here, that signal needs to propagate through it fast enough. And of course, if you're dealing with an FPGA, kind of like a computer, you have to take into account, you have to convert an analog signal to a digital signal and then figure out how long it takes to go through the algorithm and convert it from digital to analog and back. So yeah.
related to this, when you mentioned that we can add filters in parallel, I wonder what happened to the effective Q of your resonator. Because
Yeah.
if I use board in different modes and you just add them, wouldn't that just cause the same lag and just spread out in more modes?
Yeah, it's a really good question. I might ask you to clarify. So, but my understanding is right. So you have a Q of this cavity. So what's the Q in this situation over here? So the effective Q is related to how long it takes for the signal to come back around. Is that what you were? Maybe we can.
Yeah.
Yeah. So it's not, and it's not related to this filter Q really. It's you want to calculate what the timing is.
Yeah, I guess if I just think of like adding a bunch of RLC components in series, it's going to affect the Q as you add more, even though you can think of them as parallel.
Yeah, so that I had the same confusion too, because I was thinking like if we're adding filters and stuff, like where is the Q coming from? Because here it's very obvious. But the Q here, it's not like the Q of the filter, and it's not the Q. This is not like an RLC circuit, and you say, okay, that is the Q. The Q is actually, it's like an effective Q, and you have to think about the timing of how long the current takes to come back around and build up. Because here, the higher your Q, you can think of it in terms of putting photons into the cavity and how long they bounce back and forth. So if the Q is really high, they're bouncing back and forth a long time before they go to an axion. So it's sort of a measurement of how easily you can build up the power. So that's more what you want to think about here. You don't want to think about like the Q of this filter. I don't know if that makes any sense. We still need to like write this up in a paper and try to explain.
It's all came to give a talk on it.
He did?
Yeah.
Who did?
It's all,
Yeah.
I think it's before.
Any other questions?
Yeah.
Other maybe more practical questions. I mentioned early on that when you see something, you want to make sure it's not an RF interference signal. I was wondering how RF interference signal looks like in your detector.
Yeah.
It also looks like a tree where you can.
Yeah, it can just look like a peak because basically this is just a giant AM radio that's very sensitive. So if there's if there's some radio station or someone has a Bluetooth phone turned on, or there's someone opens a microwave, like any of that is just RF, an RF signal that could be detected in this. So I think, yeah, and a lot of Wi-Fi is like in the 2 gigahertz range. And of course there's 5G. So there's like it could just show up as a peak in the spectrum. Another thing is like if you have noise that's internal to the to our lab or like our receiver chain, one way you would know it's that and not an Axion is if it's not enhanced on the resonance. So something that comes in the cavity would be enhanced on resonance, but if it comes in somewhere else, it's not.
Really quick related to that, if we're like operating under the assumption that axioms are just everywhere all around us, can you not just put your whole detector in a big Faraday cage and kind of eliminate all that stuff?
Yeah, you could eliminate that stuff, but practically there's actually, I don't think we have enough of it to really warrant the effort.
That's fair.
Because we're able to really eliminate a lot with the techniques that we have, and we can implement them fairly quickly. So yeah, we basically take data and we sort of set some the rate of data taking according to how many candidates we'd expect, and we try to set it so it's a reasonable number of candidates, and so you can predict how many you expect from just statistics alone. And then if you add RFI on top of that, usually it's like, I would say not more than like 10 signals per nibble, which is like a 10 megahertz this range. And a lot of them we can definitely like just narrow down based off of this stuff. Usually the biggest way of narrowing it down is we retune over that region. And then if it's gone, we say it's not an Axiom.
Okay.
Yeah.
All right, if not, then thanks Chelsea again. And thank you all for coming.